Alright, so in this video, we're given a persistent function and it wants us to do A, B, C, D, and E. If you need to, pause, read, keep up, okay? Other than that, I'm just gonna get started. So here, we're given an xt function, which is 2 t cubed minus 18 t squared plus 42t. So I used decimals on the World Wide Web there, and I graphed this particular function for you, and I cropped it based on what I thought was significant. So it kind of does this upward hump and then it dips a little bit and it reverses direction and accelerates away, okay? Which I'll show you later when we get to decimals. Other than that, let's go ahead and get going. Part A wants us to draw a diagram. Well, how do you know how to draw stuff? In order to draw stuff correctly, all you have to do is look at tangent lines. Okay, so if we look at this particular xt graph, once you plot on decimals, you should get the same graph as I do here. So this graph starts at the origin. I do want to point out that at times equal to 0 for this particular problem, xi is also 0. However, vi is not 0. Okay, so just because the initial position is 0 does not mean that the initial velocity is 0. Well, how do you know whether the initial velocity is 0, a negative value, or a positive value? All you have to do is extend the line that crosses, this t-axis here. Okay, so visually, I'm just going to go ahead and draw a tangent line. So I'm going to extend that graph itself, to the left side of the t-axis. We just don't use negative t in physics because time can't be negative; it's a scalar quantity. However, this graph itself in mathematics continues on the left side. Okay, so the fact that I can draw a tangent line at the origin here, and this is a positive slope tangent line, tells me that my vi is indeed positive. So it's not 0; it's some number. I don't know what it is. I just know that it's initially moving in the rightward direction, okay? Well, how do you know whether it's moving at a constant rate or speeding up or slowing down? All you have to do is just draw a few tangent lines and just kind of see the slope of the tangent lines itself, okay? So here's another one. This is my v of t at some point in time. Here's another v of t at some point in time. So all I know is that if I just look at these first 4 tangent lines, you can see that the slope itself is getting more gradual, or it gets less steep, meaning that it's slowing down as it's moving to the right. All right, it's positive velocity, so it's moving to the right, but it's slowing down because the tangent line keeps getting more gradual. It eventually approaches 0. So at the peak here, the object changes direction. So the tangent line is 0 because in order for an object to change direction, it must come to a stop momentarily. Okay. So right away, this first segment, I can definitively know that the object is slowing down as it's moving to the right. Okay, so I can draw this motion. Well, I want to start with some big arrow or just some arrow point to the right. How big doesn't really matter. It's up to you. And then as time increases for the first second and a half or so, the velocity gets smaller and smaller and smaller. Eventually, it comes to a stop. Right. So I'm done with this first part of the graph. And then you notice here it turns around and changes direction. So it was moving to the right, but now it looks like it stops at about, let's say, like 29 and a half, and then it starts to move backward. Okay, so I'm just going to draw another tangent line. But you notice here this tangent line is kind of gradual, but more importantly, it's the tangent line here has a negative slope, right? So I'm just keep drawing it. The negative slope gets steeper, and it kind of tapers off right there, and then it gets gradual again, right? So it stops here, picks up speed again in the negative direction, kind of keeps it going at a constant for a little bit, and then decides to slow down and eventually stops again because the tangent line at any vertex, right, or peak here is going to be 0. Okay, so information that I can pull out that I hope you're picking up is, well, this whole entire second segment is moving to the left. It's negative because all of these tangent lines are negative slope. It's just it was first getting steeper in the negative direction and then it tapers off. So it speeds up in the leftward direction, tapers off a little bit, and then slows down, but still moving to the left. It eventually comes to a stop. Okay, so it already stopped here and it changed direction. So therefore, the next set of arrows I want to do is I want to draw a speeding up because, like I said, it gets steeper and then it gets gradual. So speeding up, slowing down. So these arrows are going to come up. They start off, kind of short, but moving to the left, and then it gets longer and longer because the object is speeding up, and it tapers off right about there, and then it slows down, and then it comes to a stop, right? So I'm almost done with the whole entire motion. But once it stops, though, as you can see here, right about in between, about at about 4.5 seconds, right? It stops. and then it changes direction and accelerates to the right. Okay, I know it accelerates to the right because, well, this is a curved graph, right? So therefore, I can just draw a bunch of tangent lines again, and as you can see, these tangent lines have a positive slope, meaning it's moving to the right. So positive is moving to the right, negative is moving to the left. Well, it's speeding up here because the slope of each of these tangent lines keeps getting steeper and steeper. So I can, again, for sure say that it's speeding up, okay? I don't know what rate, I just know that it's speeding up. So therefore it stopped here. Now it's gonna go back to the right. So I'm gonna start small and it gets bigger and bigger and bigger because the velocity is getting faster and faster. So that's what it looks like. So we can say that object is initially moving to the right and then decelerating and bring us to a stop. And once it stops, it accelerates to the left. And then it decelerates as it's moving left and then stops again. And then accelerates to the right and keeps on accelerating until whenever, okay? All right, so that is the motion diagram for part A. Part B is super easy. All you have to do to find the velocity, just take the derivative of the x of t function. So here I have v of t is equal to dx over dt. X is given to us as 2t cubed minus 18t squared plus 42t. So if you take the derivative of this correctly, you should get 6t squared minus 36t plus 42. Okay, so hopefully you know your power rule for derivative. And then once you have this velocity function, well, all you have to do is plug in 3 seconds and it tells you exactly how fast you're moving. So here, I carry the 6 down, wherever t is, I just plug in 3 seconds. 36, t is right there, plug in 3, 42 is just the coefficient. And then if you simplify that on your calculator, you should get a value of negative 6 meters per second. To make sure my answer kind of makes sense, I'm just going to go back on the graph here where I'm circling. There's 3 seconds. I'm just going to go up and touch the graph. And that is a negative tangent line. So therefore, my answer makes sense. It is a negative value. So hopefully my calculator works on point for that one. All right, let's do part C. Part C asks you to find when is the particle at rest. So in order to find when the particle is at rest, all you have to do is take the velocity function, whatever it is, and set it equal to 0 and see if there is a solution. So here's my velocity function that I just derived from taking the derivative of your x and t function. So here's v of t. This is 6t squared minus 36t plus 42. I'm going to set the whole thing equal to 0. Well, why? Because when an object comes to a stop, it's not moving. If it's not moving, its velocity must be 0 at that moment. Okay. So as you can see here, on the right side, it kind of looks nice. You know, it has this format of a quadratic, function. This is 6t squared, and then it's minus 36t, and it's got some coefficient here. So the highest exponent here is t squared, and you got a t term by itself, and then you got some constant. So right away, I hope you recognize this is just a quadratic function. So here, my a is 6, my b is negative 36. Don't forget, there's a negative sign here in front of the 36, so don't forget about the signs in front of these numbers, okay? Otherwise, when you do quadratic, you goof. And then C here is a positive 42, because there's a positive sign in 42. All right, so rather than doing quadratic by hand, I'm just going to use a quadratic solver, which I hope you have on your calculator. And if you do that correctly, you should get a value of 1.59-ish and then 4.41 seconds. So it tells me that the object stops at these 2 points during the motion, okay? And then I'm going to exit the screen real quick because I have it loaded. So I'm just going to help you use a quadratic solver. So if you're practicing at home, you can use this on free online app. So here is the quadratic solver, right? All right, I preloaded these coefficients for you. A was 6, again. Make sure you put a negative 36 for B, and then C was positive 42, and just hit calculate, all right? And then it'll output your answers. So here my x value is, as you can see on the screen there, is 4.41, and then my other time is 1.585. I just round to 1.59, and that's it. That's where those values come from, okay? So use a quadratic solver on your calculator and just move on with life. All right, let's get back to this. Let me run through this again. All right, so once I have these, I'm just going to plot it on the graph here, right? So 1.59 second is about there, which makes sense, right? Because if I just drew this dashed line, it meets kind of the peak there where I know that the V instantaneous at that moment is 0. And then 4.41 is about there, right? Just eyeballing it, my answer makes sense because the V here is also 0. So on this graph, the first peak occurs at about 1.59, and then the second valley here occurs at 4.41. So those are points where the object stops and changes direction. All right. Let's move on to D, E, and F. Part E asks you to find the acceleration at 4 seconds. This is pretty light work. Well, to find the acceleration, all you have to do is derive your velocity function. So A of t is equal to dv over dt. But the velocity function here was already calculated by deriving x of t. So I just carry that work over. So if you use, once again, power rule, A of t is going to equal to 12t minus 36. Okay. So I do want to point out here, as you can see, A of t here is 12t minus 36. The fact that there's a t here tells you that A is not a constant for this problem, right? Because as time changes, A changes. So by looking at this graph, your A varies as a function of time. All right. But now that we have A, all we have to do is plug in 4 seconds, right? The 12 I carried over, t I just plug in 4, and then the negative 36 I just carried over. And if you do that correctly, at this moment in time, at 4 seconds, your acceleration is a positive 12 meters per second square. Okay, again, A is not a constant. It just happens to be positive 12 meters per second square at 4 seconds. Okay, it varies as a function of time because the function, again, has a t in it. All right, let's move on to part E. Part E asks, when is the particle moving forward? Well, in order to figure that out, it's pretty light work. I mean, I hate to say it, all you have to do is look at the graph. You know, is your position moving to the right on the number line or moving leftward? So I put on these two time values because I know this is where the object changed direction at 1.59 seconds and at 4.41 seconds. So to moving forward is this segment here. Why? Because on the number line, right, the object starts at xi is equal to 0. Its initial position is equal to 0. And then it keeps moving to the right and got to almost about 30, you know, positive 30 here, and stops. Once it stops, though, it started moving left. But the question is moving forward in the positive x direction. So right away, my answer would be from 0 to 1.59 seconds. I don't care about this next segment because this segment is moving leftward. However, what I do care about is the object stops again at 4.41 seconds, and then watch my cursor, and then it starts to move to the right, right, or upward on the x of t statement here on the vertical axis, right? So it looks like it stops at, say, about, what is this? I don't know, 7, right? Because these are increments of 2. So at about 7, it starts moving to the 8, 9, 10, 11, 12, 13, all the way to infinite, whatever it is, you know, however far you want to go. So those are the two segments in which the objects are moving forward. So I'm just going to split it up. So I can say that objects are moving to the right from 0 to 1.95 seconds. And then I'm going to skip this middle segment because it was moving leftward. And then the next part of the time would be from 4.41 seconds to infinite, right? And I put infinite because I graphed it and it kept going. So let me just exit the screen once again, and then let me show you this. All right, so here's the graph. Again, as you can see, I plotted the function here. And if I keep zooming out and zooming out and zooming out and zooming out, as you can see, the function never quite turned around again. Okay, so it keeps on going and going and going, right? So therefore, I can safely say that it's from 4.41 to, infinite amount of time, okay? Let me get back to this. So that's that. Let me go ahead and fast forward all this beautiful work again. And then just move on to F. For part F, it says when is the particle speeding up and then when is it slowing down. So to figure out when it's speeding up and slowing down, I have to figure out whether A comes to 0 or not, because as you can see here, A actually changes direction. So here in my work, I just solved for A. I set A equal to 0. I found A is 0 at 3 seconds. So why is this important? An object reaches maximum speed when acceleration stops, right? And acceleration can change direction. So therefore, at 3 seconds, as I said earlier, just based on the tangent line, I know that it kind of tapers off, aka it stops accelerating, which means it moves at a constant velocity for a little bit. Well, at what time? That would take place at 3 seconds based on this graph because I just solved for it. Now, why is this important for part F? You're looking for when the particle is speeding up, right? And when is it slowing down? Well, if you kept up already earlier in the previous slides by analyzing tangent lines, right? This part here, the object stopped and then it accelerated, aka speeding up to the left. So it just says speeding up. It didn't say left or right. So this segment fits. So from 1.59 seconds to 3 seconds, it is speeding up, okay? In addition, this also is speeding up, right? Because the objects came to a stop at 4.41 and then accelerated to the right. So it's speeding up to the right. So I want to clarify. This blue segment here is speeding up to the left, but the key is just speeding up. Now, this right here is speeding up to the right. Because it only asks for speeding up, I want to highlight both these segments, okay? So if a question asks you, where is it speeding up leftward? So you would only give this answer where my cursor is kind of, tracing back and forth here. If it asks you, where is it speeding up, moving to the right, then it would just be the orange. However, it's just saying speeding up, and it didn't specify a direction, so I want to include both of these portions, okay? Now, the next portion here says, when is it slowing down, right? Well, it's slowing down in the first segment here. So if you kept up with the first part where I drew the motion diagram for you, the initial velocity was positive, and then the tangent line keeps getting more gradual and more gradual, and it eventually comes to a stop. So from 0 to 1.59 second, it is slowing down, right? Okay, so that's that. And then here from 3 to 4.41 second, it is also slowing down. So from 0 to 1.59, it's moving to the right and slowing down. From 1.59, no, excuse me, from 3 to 4.41, it is slowing down as it's moving leftward. So those are your answers, okay? So I just made a note for you here. Tangent line gets steeper, it's speeding up, and then tangent line gets flat, it's slowing down. So to clarify, the answer for the second part of F would be it is slowing down from 0 to 1.59 seconds, and also from 3 to 4.41 seconds. And that is all for this video. I hope that helps. Stay nerdy. Don't be whack.